Hello friends, so this lecture we will start a new topic which is tension members. So tension members with respect to steel structures are one of the most important topics, and it is one of the most important topics with respect to gate as well. So we will see firstly what is the basic understanding of a tension member, and then we will progressively go on seeing what are the modes of failure, what are the different kinds of failure, and how to restrict the different kinds of failure, and what are the different methods of calculating the strength of a tension member. So essentially, as the name suggests, a tension member will be a member that will be subjected to only direct tension forces. Direct tension forces means it will carry only tensile stresses, or it will resist only tension forces due to directly applied tensile forces axially. Which means if there is a member, suppose this is a bar or a rod, and this is the axis of the member. So if there is a tension force acting along the axis of the member axially, that means this member over here, it is subjected to tension force directly due to the action of a tension force. There is no bending moment, there is no torsional moment due to which a tension force is coming. Due to the direct application of a tension force, a tensile stress will be induced in this member. So this tension force is acting directly along the axis of the member. So for a tension members, that it should be acted, or it should be subjected to direct tension forces acting along the axis of the member. If this is the loading criteria, then it becomes a tension member. And the strength of a tension member, it depends upon many criteria, out of which I have listed the main and the most important criteria. The first is the length of the connection. Each and every topic, each and every factors on which the strength depends, we will later on see it in a much elaborate way in each and every lectures. But for now, I will give you a basic introduction about what is length of a connection, or how does these factors affect the strength of a connection. So strength of a tension member, the first point, it depends upon the length of the connection. So length of the connection means, suppose a member angle or a plate is connected to another plate which is subjected to a tension force. So the total length of the connection will give you what is the meaning of the length of the connection. So that length of the connection, if that length of the connection is more, the tension strength of the member will be more. So suppose this is a plate, it is connected to another plate. This is a plate, it is connected to another plate with the help of some bolts. So this is the portion where these two plates are connected. So this is known as LC, or length of the connection. So higher is this length of the connection, more uniform will be the stress distribution, and hence more effective will be the strength taking capacity of the tension member, or more effective will be the joint. So therefore, if the length of the connection is high, or if it is more, you can say that the redistribution of stress or the stress distribution, it becomes uniform, or it becomes much more to the uniform side. So therefore, what happens? The strength taking capacity of the tension member increases. So higher the length of the connection, more will be the strength taking capacity of the tension member. Now size, shape and the spacing of the fasteners. This is a very important topic, a very important part which is actually indirectly related to the strength of the tension member. Size, suppose fasteners, generally we are using the fasteners as bolting. Bolting is generally used. Riveting is obsolete nowadays. Bolting and welding is the most commonly kind of fasteners that are used. So in case of size, so size will refer to the size of the weld as well as size of the bolting as well. So if the size is more, it means that the hole will be more. So if the size is more, on one hand it may happen that your net sectional area will decrease, but on the other hand, since the size of the fasteners is more, so it will contribute to the increase in the strength as well. Shape, or the shape depends upon whether the shape of the, suppose the bolting, whether the shape of the bolts are it is hexagonal, or it is square, or it is pentagonal, depending on that. So this shape of the fasteners has a very limiting impact on the strength of the tension member. But out of these three, the spacing of the fasteners has a very direct impact on the strength of the tension member. If the spacing is very high, if the spacing is very more, then the strength of the tension member will decrease. because if the spacing is very high, then the area or then the portion between the fasteners, they will be subjected to high elongation or high deformation due to the impact of the tension force. As a result of which, due to the high deformation or high elongation, it will become unserviceable. So, if the spacing of the fasteners is high, due to unserviceability, your tension member might become inefficient. This is the impact of size, shape and shaping of the spacing of the fasteners. Now, next is the net sectional area of the tension members. Now, for the net sectional area of the tension members, the higher will be the net sectional area, the more will be the strength of the tension member, because you can see that if this is a tension member, as we have seen in the first point, the direct tension force is acting directly along the axis of the tension member, or the force or the tension force, it is acting axially along the it is acting axially of the tension member. That means the tension force that is acting, it is acting axially. So therefore, this cross-sectional area is actually the area that is resisting the tension force, or that is providing a resistance to the force. So therefore, higher will be the net cross-sectional area, more will be the tension strength or the strength of the tension member. This all topic we will discuss in a separate lectures elaborate way, but this is just a brief introduction. Eccentricity. As we have seen in the bolting conditions also, if the eccentricity is high, then the impact of the loading will be also high, because if the eccentricity is high, then the externally then the moment that is induced due to the eccentricity, that moment, either it is a bending moment or it is a torsional moment, depending upon the plane of the loading. So that moment will be high. So if that moment is high, that means an extra load has been imposed on the structure apart from the vertically applied load. That is the eccentricity. So therefore, load plus the moment, so external additional load. So if the eccentricity is high, the total load increases and hence the strength taking capacity will decrease. Because if the eccentricity is high, the additional moment that is induced in the structure due to the eccentricity will be more, and hence the strength taking capacity will decrease. Fabrication. Now fabrication depends on two types, whether it is a shop fabricated or whether it is a field fabricated. Shop fabricated means it is fabricated, or the fabrication or the assembling of the tension member is done adhering to the codal provisions, that is adhering to IS 800 and also adhering to the specific codal provisions as per the fasteners. So therefore, if the fabrication is done in the shop, we assume or we see that, or it is customary that the conditions will be as per the codal provisions. That means the deviations from the codal provisions will be very minimum, or the standard deviation will be very minimum. So therefore, for a shop fabricated member, the efficiency or the strength will be essentially high. But for a field fabricated member, where the work has to be done in a very short span of time and where the adherence to the codal provisions is not so much high, so therefore the standard deviation is high, and hence the strength of the tension member, if it is field fabricated, it will be lesser than the shop fabricated one. Then the last and one of the most important is the shear lag at the end connection. Okay, so if the shear lag is a factor which comes when there is an angle or a channel or a T-section, if it is connected to another member in order to form a compound tension member, then shear lag at the connection end is introduced. Now due to this shear lag, there is actually a non-uniform distribution of shear stress in the connected part of the member and in the unconnected part of the member. Okay, so due to this, what will happen, due to the non-uniform distribution of the shear stress in the connected part of a member with respect to the unconnected part of the member, so due to this non-uniform distribution, there is a lag. There is a lag in the shear resisting capacity. So that lag is known as shear lag at the connection end. So if the shear lag is high, it means the non-uniformity in the shear stress distribution in the connected part and in the unconnected part is high. So if the non-uniformity is high, that means the unconnected part, it is not efficiently taking up the stresses it should take or it is designed to take. So therefore, if the shear lag at the connection end is high, you have to know that the tension member is inefficient. The tension member, the strength of the tension member is lesser than it actually should be. So from all these 6 factors, we have seen that if the length of the connection is high, the strength of the tension member will be high. The size, shape and spacing, we have seen that if the spacing is high, then what will happen? The strength of the connection member will decrease owing to larger deformations. Next sectional area. If the next sectional area is high, the tension member strength will be high. Eccentricity. If it is high, the additional moment induced will be high and hence the strength taking capacity will be lessened. Fabrication depends upon two kinds, whether shock or field. If it is shock, it will be high. If it is field, it will be less. Shear lag in the connection end. If the shear lag in the connection end is high, it means the non-uniformity is high and therefore the efficiency of the strength, efficiency of the tension member is lesser than it should be in actual. So these are the different factors on which how it depends, the strength depends. Now let us see what are the different kinds of members which can be classified as tension members. Wires and cables. Now you have seen wires and cables in cable stayed bridge or in cable suspension bridge, as you have the Bandra-Wallis link. Okay, so these are the wires and cables which are subjected to tension. So these are members which are subjected to direct axial tension force. So these can be also classified as tension members. Then bars and rod. Any kind of bars and rod, these are also subjected to direct axial tensile forces. So these are also tension members. Then rolled sections such as angle, channels and T-sections. So this is an angle section. So this angle section can also be used as a tension force. If you as a tension member, if you apply a tension force that is acting along the axis of the member, so this member can be used as a tension force. Then this is a T section. This is a rolled T section. This can also be used as a tension force. This is a rolled channel section. This can also be used as a tension force. Then is the compound sections. Compound section or built-up section means the assembling of different kind of individual section to form a different compound structure. Suppose if there are two angles which are merged together or which are jointed together to form a different structure which also behaves as a tension member, then it is known as a compound or a built-up tension member. If there are channels, there are 2 channels or 3 channels which are used and which are jointed together in order to form a compound structure which behaves as a tension member, it will be known as a compound section. So likewise, this is a compound or a built-up section is a section where 2 or more individual rolled steel sections, are jointed either by welding or by bolting or by riveting to form a bigger compound structure which can be either used as a tension member or a compression member, is known as a compound or a built-up section. Here in the tension member, it will be used as a tension member. So you can see this is a very simplified compound section where 2 angles are connected back to back, maybe with the help of welding or bolting, whatever be the design case. So this is a compound section. This is also a compound section where 2 channels are placed back to back in order to behave as a tension member. This is also compound sections where 2 channels are placed at the tip diagonally. It can also behave as a tension member. Okay. So compound section is a section which we can build by jointing 2 or more individual rolled steel section, depending upon what kind of design section, depending upon what kind of design criteria we have. So therefore, this is the basics of tension member, and this is the basic ideology that the tension member will be always subjected to axially applied tensile load. These are the factors on which the strength depends, and these are basic examples of a tension members.